Okay, welcome everyone to the 59th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Liran Shaul from Charles University, Prague, and he'll be talking to us about finitistic dimension, generation of injectives, and dualizing complexes.
Okay, thank you very much for the invitation to speak here. To explain what this talk is about, let me start with a classical theorem of Grothendieck from the 1960s, which says, well, it says something a little more general, but for our purposes, it says the following. So let A be a commutative noetherian ring. And suppose it has a dualizing complex. I will soon recall what these are. Then the dimension of A is finite. And basically the goal of my talk is to explain how this result remains true for non-commutative rings. Okay, there are several things to say about this. In particular, the most pressing question, I guess, is what do I mean by dimension in this case? Sorry, I have. Right. So I want to get some notion of dimension for non-commutative rings. And the way I want to get to it is via homological algebra. So we want to use homological algebra to define the dimension of a ring, which might not be commutative. And probably the most obvious way to do this, or the most naive way, is to use a global dimension. So the global dimension of a ring is given by, let's say, global dimension of A is this formula. So I look on all A modules and I take the supremum of projective dimensions. And indeed, for commutative rings which are regular, this coincide with the usual dimension. So this is nice. Sorry, I have a problem. Okay. But the problem is that this is, of course, too restrictive because if A is, let's say, the ring of dual numbers, and this is a very simple ring, but the projective dimension of the field itself is infinite. So the global dimension of this A is infinite. So this naive way of defining dimension doesn't work, and for this reason, Kaplansky already in the 1950s suggested to replace this by using finitistic dimension. So as an alternative for this, we have the following. So for a ring A, its small finitistic dimension is defined by the supremum among all finitely generated modules which have finite projective dimension of the projective dimension of these A modules. And similarly, for ring A, its big finitistic dimension is given by, so I just take the supremum of, sorry, this is wrong. The supremum of projective dimension among all A modules of finite projective dimension. In particular, in this example, if A is this ring of dual numbers, then you see for this ring, every A module is a direct sum of K and A. So it follows that these two numbers are actually zero. So in this sense, this dimension captures the simplicity of this ring better. And so if I want to calculate this alternative homological dimension, these finitistic dimensions, we have the following results. So the first one is just the Utlander-Buchsbaum formula. So this is 1957, and it says that if A is a local ring, local noetherian ring, then the small finitistic dimension of A is just the depth of A. And a little after that, Bass showed in 1962 that if A is a commutative noetherian ring, and if N is a number which is at most the Krull dimension, then there is an A module M with projective dimension being equal to N. So in particular, this big finitistic dimension of A is at least the Krull dimension. And so for 10 years, it was conjectured that the converse holds as well. And indeed, we have from 1971, Renaud-Grousson, that for a commutative noetherian ring, the big finitistic dimension of it is the Krull dimension. So in this sense, I can think of this big finitistic dimension as a generalization of Krull dimension, which gives me a nice theory of dimension for noetherian rings. So once we know, once we understand this for commutative rings, and indeed this theorem of Renaud-Grousson completely solves the commutative case, it's time to ask, what about non-commutative rings? So for non-commutative rings, here the situation is much more complicated. So let me for now restrict ourselves to Artin algebra. So let's recall that an Artin algebra is a ring which is finitely generated over an Artinian commutative ring. And for this, we have the following conjectures. So the first one says that there is an equality between the small and the big finitistic dimension, and the second and the third says that these numbers are finite. So these conjectures were probably originated around the 1960s, probably asked first by Bass. It's not clear who made them into conjectures, as far as I know. The first of them, number one, was disproved by Zimmermann-Huisgen in 1992. In fact, it is false even for finite-dimensional algebras over a field. So finite-dimensional algebras over a field are the most prominent example of Artin algebras, and usually people work on these problems of finite-dimensional algebras, although you can ask these questions for much more general classes of rings. So, for example, I want us to notice that a commutative Artin algebra is just a commutative Artinian ring, so it has Krull dimension 0. But of course, we can ask these finiteness questions not only in dimension 0 in the commutative case, so you can ask this also in the non-commutative case and ask which noetherian rings have finite finitistic dimension. Now, of course, if number 3 is true, the number 2 is true. So these are known as the small and the big finitistic dimension conjectures. And they are still open. And I also want to mention that besides being a very natural question to ask, a very basic homological question that we don't know how to answer, there is another reason why these conjectures are so important, namely they imply many other conjectures. Namely, if the finitistic dimension conjectures are true, many other conjectures are known to be true. For example, my favorite one in this setting is probably Gorenstein symmetry, which says that if A has a finite injective dimension as a left module over itself, then it has finite injective dimension as a right module over itself. And it is known actually that, so it's not, you can ask this, for example, also for any noetherian ring, whether it's true. As far as I know, there are no counterexample for this conjecture for noetherian rings. But it is known that if your ring has finite finitistic dimension, well, on the right side, let's say, then Gorenstein symmetry does hold for it. And there are various other such conjectures, such, let's say, the Uslander-Reiten conjecture, the generalized Nakayama conjecture, etc. And these follow from the finitistic dimension conjecture. So not only it's a very natural question to ask, it also implies many other very, very nice facts about rings, let's say about art in algebras at least, that we would very much like to know. So in this sense, this I think is one of the key open problems in homological algebra. And so following ideas of Rickard and Keller, I would like us to turn our attention, well, also because following the title of this seminar, I want us to turn attention to the triangulated category, which is the derived category associated to the ring we study. So perhaps just as a warm-up, I want to mention the following proposition, which is quite easy. So for a ring A, consider the following triangulated category. So this is the thick subcategory generated by injective A modules. So what does it mean? It means that I consider all injective modules, and then I look on the smallest thick triangulated subcategory, which contains them inside D of A. Then it's quite elementary to notice that this category is equal to the bounded derived category of all bounded complexes of A modules, if and only if, well, if and only if every module has finite injective dimension, or put it another way, if and only if the global dimension of A is finite. So I see that by looking on what my injective modules generate, I can deduce something about the global dimension. Of course, it doesn't matter if I write here injective modules or projective modules. These are equivalent in this case. And it's quite fantastic that we can achieve a similar theorem for finitistic dimension. So it is entirely not obvious, but true that often we can get something similar for finitistic dimension. And as far as I understand, the history of this is that in 2002, Keller noticed that if I look now on something bigger, namely, I look on the localizing subcategory generated by the injective, which means that I allow now also infinite direct sums or infinite coproducts. And so I look on the smallest triangulated category, which contains injectives and is closed under infinite coproducts. So this is some triangulated subcategory of the derived category, and I can ask whether this is everything. And what Keller noticed is that if this does happen for a finite-dimensional algebra over a field, then many of the homological conjectures follow. And then he asked, is this true for finitistic dimension, for the finitistic dimension conjecture? And indeed, so we have this result of Rickard from 2018, which says that if A is a finite dimensional algebra over a field, and if the injective modules generate D of A, then A has a finite finitistic dimension, big finitistic dimension. So the way I view now this result is that if I go back here, so I would like to think that these two results, they are essentially the same. So to explain this, let me first mention that, okay, we know already that for commutative ring, this Krull dimension, this finitistic dimension, they are the same. So the conclusion is the same. Okay, but here we have a condition that a dualizing complex exists. Here we have two conditions, namely finite dimensional algebra, and the localizing subcategory generated by the injectives is everything. So maybe as a first step to connect these, let me mention that it follows from the Hopkins-Neumann classification of localizing subcategories of D of A, where A is a commutative noetherian ring, that, and I would also call this Hopkins-Neumann essentially, that for a commutative noetherian ring, indeed, this equality holds. Okay, so for a commutative noetherian ring, this condition is automatic. And then the only thing I want to say now, which is, I think, quite obvious, is that finite dimensional algebras have dualizing complexes. In a minute, I will, again, as I said, I will explain more about these dualizing complexes. But I think that once you get the picture of all these results, you can also already start seeing that these two results, which are almost 60 years apart, they are essentially the same kind of result. And maybe it's worth mentioning that I'm not the first person to notice that this result of Grothendieck is something about finitistic dimension. Indeed, after this result of Renaud-Grousson from 1971, so their paper, their proof is of this equality. Well, essentially what they prove is that if you have a module of finite flat dimension, then its projective dimension is at most the Krull dimension, and their proof is very difficult. For example, they needed to invent the notion of a Mittag-Leffler module in order to prove this, and it's quite deep proof. We actually ran mini seminar on it in my research group. We learned all the details. It's quite difficult. In any case, about 10 years later, Foxby gave a new proof of Renaud-Grousson. Well, in a specific case, for commutative noetherian rings with a dualizing complex. Because he essentially observed that in this case, you can use the properties of the dualizing complex to give a much easier proof of this fact. And so what I want to explain today is how Foxby, Grothendieck, Rickard, they all did essentially the same thing. That's my view of it anyhow. So to proceed, let us recall a bit about dualizing complexes in possibly over a possibly non-commutative ring. And so this is something which is almost classical by now. So let me start with the very, very classical case. So if K is a field and V is a finite dimensional vector space over K, then the natural map this map is always an isomorphism. And so the basic idea then is that we want to generalize this to rings which are not fields. Okay, I will explain two generalizations of this, but let me start with the first one. So for a noetherian ring, let's say left and right noetherian ring, a dualizing complex over A in this talk will be the following. So it will be a complex of bimodules over A, denoted by R, with the following properties. The first one is that it is bounded and has finitely generated cohomology, both as a left module and as a right module over A. The second condition is that for each n, I have that the nth module is an injective module when restricted to either A or A opposite. So when I consider Rn, when I forget it's a bimodule and only look on it as a left or as a right A module, in both cases I need to get an injective module. And finally, I wanted the natural maps, what called usually the homototy maps, so from A to home from RR, and from A to home RR over the opposite ring. This should be our quasi-isomorphisms. Right, and so in terms of history, I would say that this was first defined by Grothendieck for commutative rings and Yekutieli in the non-commutative case. And maybe a key example is that if A is a finite dimensional algebra over a field K, then the dual module, namely home over K of AK, is a dualizing complex over A. But the point is that there are many other rings which have dualizing complexes, and I would dare to say that most rings that arise in nature have dualizing complexes. So it's not something which is restricted to finite-dimensional case. It's far more general. And maybe about the name, or how does this generalize this classical case of duality of vector spaces? Well, you see, if you have a dualizing complex, so if A has a dualizing complex R, and M is a finitely generated A module, the natural map, this natural map is an isomorphism in the derived category. So the natural map from M to its double dual taken with respect to the dualizing complex, is always an isomorphism. I don't even need derived home here because of my injectivity assumption, but let's leave it like this. Okay, so this is nice and all, but actually to use dualizing complexes in our contexts, restricting things to things with finitely generated cohomology is just not enough. I need to work, I want to work with finitistic dimension, which is big finitistic dimension. So I cannot possibly restrict myself only to finitely generated models. So then the question is, how can you extend this duality for infinitely generated things when we know that even for finite dimensional vector space over a field, even over a field, this doesn't work, right? If I take here a vector space which is infinite dimensional, this map is usually not an isomorphism. Well, luckily, there is an answer to this. So for this, we need a little more of the theory of triangulated categories. So for a triangulated category C, let me denote by C omega, it's a full triangulated subcategory of compact objects. So here's a couple of theorems. So this theorem is due to Krause from 2005. And it says that if A is a noetherian ring, then there is an equivalence such that the compact objects of the homotopy category of injective A modules is equivalent to the bounded derived category of finitely generated A modules. The second theorem I want to mention is from the same time. It's Jorgensen, also 2005. And it says that if A is a noetherian ring with a dualizing complex, there is an equivalence of the compact objects in the homotopy category of projective modules with the opposite category to the bounded derived category of finitely generated right A modules. Now, notice that, as I mentioned here before, for finitely generated modules, or a bit more generally for bounded complexes with finitely generated cohomology, a dualizing complex induces an equivalence from the bounded derived category to the opposite one over the opposite ring. So in other words, what we see here is that the dualizing complex induces an equivalence between the categories of compact objects in the categories of homotopy category of injectives and the homotopy category of projectives. So then a natural question is, does this equivalence extend beyond just the compact objects? And the answer is yes. So this is a very important result of Inger Krause from 2006. So it says the following. So let A be a noetherian ring, not necessarily commutative, with a dualizing complex R. Then there is an equivalence of categories. Like this. So tensoring with R induces an equivalence of categories from the homotopy category of projective modules to the homotopy category of injective modules, such that diagram this diagram is commutative. So in this diagram, the top orthogonal arrow is this equivalence. And then we have these vertical maps, which are just these equivalence of categories due to Krause and Jorgensen. And then here, the bottom horizontal arrow is just the duality induced by the dualizing complex. So going to the homotopy categories, in fact, I get an extension of this duality to the full homotopy categories of projective and injective modules. And let me mention that we can also quite explicitly describe the inverse equivalence. So to describe the inverse, recall the following result. So this is Neyman 2008. Well, you would ask how it could be later than this 2006 result, but it was already known, this result, for some rings, but Neyman actually showed that for any ring, the inclusion functor from the homotopy category of projectives to the homotopy category of flats has a right adjoint. So let me denote it by Q. And then the inverse of the above equivalence is given by this Q composed with hom over A from the dualizing complex. So if I apply hom over A from the dualizing complex to a complex of injectives, I will get a complex of flat modules. And then I apply this right adjoint and I get a complex of projectives. And this composition of functors, this is an inverse to the equivalence, which is given by tensoring with R. Okay, so now let me state the main result. So let A be a left and right noetherian ring with a dualizing complex, and assume that the localizing subcategory generated by the injectives is the entire derived category. Then the finitistic dimension of A is finite. So essentially this, as written here, is a direct generalization of this result of Rickard that we had here, where we replace the condition of being a finite dimensional algebra over a field with a noetherian ring which has a dualizing complex. But really, I tend to think of it also as a generalization of this result of Grothendieck, namely that a noetherian ring with a dualizing complex has finite dimension. Well, you only need to know also that the injectives generate. And I will say a little more about this condition later, but for now, let me try to sketch the proof of this. So to prove this, we first need the following result, which we prove using the theory of digerings. So it's a bit technical, so I will only state it and not say more. So if a noetherian ring with a dualizing complex has finitistic dimension being equal to infinity, so something that I hope shouldn't happen, then there is a sequence of natural numbers which is increasing, and a sequence of A modules Mn with flat dimension of Mn being equal to An, and such that I have non-vanishing of Tor from the dualizing complex to Mn at the degree of Tor, which is the flat dimension of Mn. So this is a bit technical. The proof of this is quite long, and as I said, it uses tools of the theory of digering. So let me take this for granted, and using this, let me try to sketch the proof of the main theorem. So I'm assuming that indeed the localizing subcategory of the injectives is everything, and let's assume that the finitistic dimension is actually infinite. Then for each n, let Pn be a flat resolution of this Mn of length An. So this Mn has flat dimension An, so I can find the flat resolution whose length is this. And then I actually follow ideas of Rickard and consider the following map, which I call phi, which is going from the direct sum of all these Pn shifted to the direct product of all these Pn shifted. And now you see, these Pn's have the property that Hn of Pn, or let's say Hm of this Pn, because this is a projective resolution, this is usually 0, except that Han, or sorry, that H0 of this Pn is just Mn. So if I make these shifts, actually what happens is that at degree An, I just get Mn on both sides here. So it follows that this map phi is actually quasi-isomorphism. I would also say that these are both complexes of flat modules. So this is a quasi-isomorphism and is a map in K flat A. However, this map is not a homotopy equivalence, which can be seen from considering tensoring it with a resolution of R, which consists of bounded complexes of finitely generated modules. You can find such because R is a dualizing complex, and then if you tensor with it, you will get the following map. And because of our non-vanishing of Tor in this technical theorem we get that this map is not an isomorphism. Because essentially I take a direct sum and direct product. In both sides I have the same modules. and they are, all of them are non-zero, so this map cannot be an isomorphism. So it follows that my original phi is not a homotopy equivalence. So it's a quasi-isomorphism, but not a homotopy equivalence. And this is really what we need. Because now let D be the cone of phi. So this D is now an acyclic complex of flat modules, which is bounded below, and it's not null homotopic. It's not null homotopic because phi is not a homotopy equivalence. And now let C be Q of D. So I'm using this right adjoint we had. So this C is in K Proj A. And some work shows that this C is also acyclic, not null homotopic, and is bounded below. And it's a complex of projectives. Now, saying C is acyclic means that I can write it as follows. So it means that all the cohomologies of C are zero, which I can write as home in the derived category from the ring A to shifts of C, or I can just write it home in the homotopic category of projectives from A to shifts of C. So now let me apply the equivalence of categories to this. And so what I get then, so from, let's say, from this, we obtain that. So from home in the homotopy category of projectives from A to shifts of C, I get home in the homotopy category of injectives from the dualizing complex to the dualizing complex tensored with A from shift of C. And this is equality, this is true for all n. Okay. And let me also mention that since C is not zero, and I applied an equivalence to it, it follows that R tensor C is not zero, because I applied an equivalence. Now, here's something else to notice. This complex R tensor C is a bounded below complex of injectives. And the bounded below complex of injectives is K-injective. But this means that this home in the homotopy category of injectives is the same as the home in the derived category. So I can write this as home in the derived category from R to R tensor C is zero. So now I can finish the proof as follows. So consider the category S, which is all the objects in the derived category for which home from X to R tensor C shifted is zero for all n. So this is a localizing subcategory of D of A, and we have just seen that R is in this category. But home from R tensor C to R tensor C is not zero because it contains the identity. So R tensor C is not in this S. So I deduce that the localizing subcategory generated by the dualizing complex is not the whole derived category. And so the only thing left to say is the following result. And it says that the localizing subcategory generated by the dualizing complex is equal to the localizing subcategories generated by the injectives. This also follows from this generalized Grothendieck duality equivalence due to Iyengar-Krause. So from this, it follows that if the finitistic dimension of A is infinite, then the localizing subcategory generated by the injectives cannot be the entire derived category. So this completes the proof of this theorem. And so now I want to maybe try to say how I like to think about this condition. So the condition that log inj A equal to d of A, what does it mean? So in my view, and it's coming from someone who works in commutative algebra, I like to think of it as follows. So over commutative noetherian rings, we know that in the composable injectives are in bijection with points of spec A. And of course, saying that loc inj A, instead of loc inj A, I can just look in the composable injectives. So the condition that in the composable injectives generate everything, it's a kind of a geometric condition. It tells you that in the composable injectives, which in my view they are points, they can see the entire derived category. So I liked, maybe it's not a good name, but I would like to say that funny definition that a ring A is called a geometric ring if this equality holds. So, for example, any commutative noetherian ring is a geometric ring. And then going back again, so this theorem of Grothendieck says that a commutative noetherian ring, which has a dualizing complex, has finite Krull dimension, and going back to our main result, assume that A is geometric. And well, finitistic dimension is dimension. So at the end of the day, I think that the result is really the same result. It says that if you have a dualizing complex and you have a geometric condition, so the indecomposable injectives see everything, then you have a finite dimension. And I'm out of time, I guess, so I stop here. Thank you.
Thank you very much, Liran. Can we all please unmute ourselves and give the speaker a round of applause? Okay. Do any of you have any questions for the speaker?
May I ask? Can you hear me?
Yeah, please.
So, you said this condition at some point, what is that? That this ring being geometric implies like this big finitistic dimension be less than infinite. Is there anything similar with regards to the small finitistic dimension?
Well, I mean, if the big one is finite, then the small one is finite.
I see. Yes, yes, yes. Okay. But nothing like some generation implies the small, just the small is finite. So I was thinking something really.
Yeah. All these results I mentioned, they were about only the big one.
I see.
But of course, it implies that the small one is always
Okay.
also finite
Okay.
in this case.
Okay.
Thank you, Francesca. Any other questions? Well, as we're waiting for the next question, can I just say something in like adding to what Francesco just said? And it has to do with this paper by, I mean, his question was, can one have a finiteness conclusion on small modules, on finitely generated modules, stemming from a generation condition? So there is a result, which is not exactly what he was asking. But since we are playing sort of word games with the word definition here, like thematically. So this result is due to, I think, Takahashi Adachi, Yuya Muzino, and Dong Yang. This is from 2018. It's a paper in the proceedings of the LMS. And it says that if dperf has an algebraic bounded T structure, then that condition, like a dperf has an algebraic bounded T structure, if and only if the algebra is of finite global dimension. This is for all Artin algebras. So an algebraic bounded T structure is defined in the following way. So we take a bounded T structure and its heart has to be a length category with only finitely many isomorphism classes of simples. So I just wanted to mention this since Francesco asked this question. Any other questions, anyone? Right. So I had a question, or rather a comment, Liran. So have you seen any evidence, or have you thought of any techniques to go the other direction? Like you start with finiteness of the FPD in your case, and then you go back to saying that either, well, in your language, the ring has to be noetherian, or whether you can say something about the existence of a dualizing complex.
I have not. I didn't think about it. You mean like saying that if the finitistic dimension is finite, then you should have some kind of generation?
Yeah.
Yeah, I don't know. I know Jeremy has something similar to this for finite dimensional algebras, but I don't know about the general case.
Yeah. Right. Okay. Any other questions? If not, let us thank Liran Shaul once again for this very wonderful talk. I'll stop recording, but Liran, hold on one second. I want to ask you one other question.
Sure.